I'd like to talk about an idea that emerged during lockdown as a convergence of a number of disparate ideas and has been co-developed since then by myself and primarily Steve Ferber. The idea is called BitBrain, and as you'll see, it also it encompasses a memory mechanism. So what is this all about? In essence, this is a mechanism that's based upon a memory mechanism and the surrounding infrastructure, which uses some ideas from sparse coding, from computational neuroscience, from information theory. There's far more detail in an upcoming paper, but background ideas have been from N of M and rank order codes, for example, sparse distributed memory, kernel methods, and various ideas from computational neuroscience, such as sparse activity and dendritic computation, homeostasis, low resolution computation, local learning, and structural plasticity. So there's a whole bunch of different ideas, and they've kind of come together. The focus has been on Internet of Things applications, really, where we can have low energy latency product for learning and inference, and also continuous learning, which carries on from the previous talk. So these are the primary aims of this idea, and the key things are highlighted in red here. Single pass unsupervised learning. We feel that the learning times and the energy used now for learning some machine learning models are becoming huge, and it seems to be that this can't go on forever. So I wanted to look at ideas where learning can be done quickly. This method uses a single pass technique for supervised learning, and the unsupervised phase, which is in advance of that, is very simple to do. The parameters are learned quickly, they're not interact, they're local, and they can be done in a highly parallel way that doesn't require global optimization or calculation of derivatives. We aim for accurate inference, which is currently a classification. It may not be to the level of the very best modern CNNs and deep neural networks, but in some cases it might be. But bear in mind, this is a very new technique, and there's a lot of work to go into it yet. There's a lot of adaptation coming up. And it's also very important that it's robust. One of the key issues, from my perspective, about artificial intelligence, machine learning, is that so many times inference can be brittle. I think if they're going to be useful in the real world, inference has to be robust. It has to degrade gracefully in the presence of noise and imperfect data and not fall off a cliff. Okay, to carry on from the previous talk, we wanted something that can support continuous adaptive learning, which might also be something that is going to be important for Internet of Things applications at the edge. It's designed to be implemented with a low energy latency product, because this is obviously increasingly important, particularly for inference. But if it learns quickly, this also means that there's a low time and energy cost for learning. And to be implemented, we've currently implemented it on conventional CPU, but we believe it'll work very well on neuromorphic devices and maybe specialist hardware as well. And we want it to be a natural target for the increasing number of event-based sensors. And as you'll probably see, this is the case. And I should say that we feel there may be some commercial interest in this. So myself and Steve filed a patent last year on the key elements of the idea. And in fact, this is the first public talk where the attendees have not been expected to sign non-disclosure agreements. Okay, so to introduce you to the idea, I want to describe something which is not necessary for the idea, but it's a very good introduction to, and I think it helps to fix ideas and show how the idea can be implemented. The idea is an address decoder element. So imagine synaptic clusters. They can be anatomical or functional. I first read about these by the work of Bartlett and Mell. So imagine now a bunch of synapses that cluster together and have a function that work together. And now imagine that these are sampling into an input space of some kind. And so you can see here, the cluster is in between the blue curly brackets, and the sampling into the input space in this case, an MNIST digit. So the input stream could be basically anything, but I'm showing using the standard MNIST digit here, which is 784 vector of 8-bit values. And now you're connected into it. In reality, these samples would be clustered more closely in this case, but it very much depends on the input type. Now, and as in very traditional networks, when the sum of the connected values multiplied by some weights reach a threshold, which is learned homeostatically, which is quite important, the address decoder element will fire. So this is analogous to an NMDA potential from a synaptic cluster within a dendrite. So how are these then used within the algorithm? Imagine now that these ADEs are collected together. They don't have to be, they could be in any cloud or pattern of points, but imagine now they're collected together into lists or vectors. And so you see the blue curly brackets here. One set goes down the rows and another set goes along the top of the columns. And the red element here is called an SBC memory. We call these, the row and column collections of ADEs, address decoders, because as you will soon see, they have a similar property to address decoders in a more traditional memory. This is a 2D SBC memory. You can have 3D and higher, but at the moment 2D is giving us good results, and of course it's easier to show. So effectively the 2D means the row and the column representation of the memory. And of course the number of ADEs in each case has to match the memory shape. It also has a third dimension, which I'll show you in the next slide, which is the depth of the memory. And it'll become obvious why you need this. So now you feed in an input into this. Now it's set up deliberately so the activation pattern is sparse. The homeostasis mechanism for the ADEs, which is learned locally in each case, tries to allow them to fire about 1% of the time. So when you put a new input in, about 1% of the ADEs will fire, both the row and the column ADEs here. And as you can see, they will have coincidences. So when a row and a column fires together, you will get these yellow diamonds, which is now, this is what we call an activated memory position in the memory space, in the 2D SBC memory space. So how do we use this for the algorithm? Just taking one column for the moment, and now I'm going to turn the SBC memory sideways. So now you can see the depth. The depth is now left to right. And you can see here we have, maybe this is for a 10 class problem, and it's one hot encoded. So we have 10 bits. And I'm only showing, obviously, the rows that have been activated by this input. Imagine this is the bits that have been set previously in the supervised learning mechanism up until now. And now a new input comes in. And this is known as class 6 because it's a supervised mechanism. We know it's class 6, and therefore we put a bit into every element of class 6 in these memory positions. So really, this is the essence of the supervised learning mechanism. It's as simple as that. You write to the SBC, you go to all the activated memory positions, and you set the relevant class bits if they have not already been set. And now conversely, for the inference mechanism, imagine now these memory positions have been activated by a test case rather than a training case. Now you go to all the activated memory positions and you count the bits that have been set and simply choose the class with the highest number of bits set. There will be definitely improvements to that, but this is the very simple basic mechanism for which I'll show you the results in a moment. And of course, this is assuming one hot encoding. If you encode the classes differently, then a different encoding and decoding process would be required. An obvious option, which we have investigated, would be N of M codes in the depth dimension. This would allow far more classes to be stored within the similar amount of memory, but you would get a little bit of aliasing, so it might degrade the classification performance slightly. Okay, so I'd like to now, having gone over what is effectively a very simple algorithm, actually, a very simple mechanism, I'd like to show you some results. And apologies to these here who don't want to see any more MNIST results ever again. I'm afraid we have used MNIST for most of these because it's a standard simple problem and everyone else knows MNIST results, so it's an easy one to describe. I just want to talk briefly about the setup used for the SBC memory here. There are 2,048 ADEs in each address decoder. Each address decoder is of a different size. So you have 6, 8, 10, and 12 as the clusters in the address decoder elements, which means that the coincidences now are between synapse clusters of different sizes. So it gives it slight flavor of a CNN or some convolutional network in the sense that you can mix and match features of different sizes in the image. The AD target firing was set at about 1% per input, so approximately 1% of your ADEs will fire on any given input. The synapse has been spatially clustered, and then there's a within-cluster structural plasticity mechanism during the unsupervised phase to home in on features. And in terms of the memories, this drives 10 2D SBCs. There are 6 full-time ones between the ADs of different sizes, and then 4 half-size ones within ADs, which means coincidences between clusters of 6 and 6, where obviously you only need half of the memory in that case, because the other half will be identical. So this means 42 megabytes for full occupancy. Typically, once the training set has gone through, you will have filled 15 megabytes or something like that. But there are opportunities here for high levels of compression. I may have time to talk about that later, if necessary. Okay, so this is some MNIST results, and I'll need to describe the setup to make it clear for you. Here, the training noise, imagine the training noise, the yellow line is the typical result you will see from any of these results. In other words, there's no training noise. This is trained purely with perfect data. The different colored lines are different amounts of training noise. This is Gaussian noise, mean centered Gaussian noise independently per pixel on the input, and it is clamped at 0 and 255. So that's the nature of the noise. And the x-axis here is the amount of noise added at the test phase. So this is to simulate a form of degradation of your inference mechanism. So this could be coming through a noisy sensor, or I mean, there's various ways you could do this. We thought Gaussian noise would be a nice, simple, straightforward starting point that everyone can understand. There are, of course, many different things you could use. This is the same mechanism I'll show you in a number of different results coming up. So you can see with no training noise, you get something like just over 97% accuracy, but then that accuracy falls off very quickly as the test noise increases. But as you add more training noise, you'll see with the red and the orange and the green, you get a small degradation at no test noise, but you get a much less sensitivity to test noise. So this is a mechanism that effectively, and if you add an enormous amount of training noise, 120 standard deviations, then you effectively don't get little difference whether or not there's no or test noise or 120. So this is a way of making the inference very robust against degraded inputs. And here's a different, just a different view of the same plot. So you can see the test in the left-hand corner is the usual case you would see. No test noise, no training noise. You can see by adding training noise, you make it very insensitive to test noise. Okay, so how does this compare to some other competitors? First of all, this is an early but respected CNN. It's designed for character recognition, but obviously certainly not state of the art nowadays. And this was trained on 100 epochs, early stopping with patience parameter of 5 and sigmoidal activations. You can see here that by the way, the error bars are standard deviations results for different random number generators, which will be probably both the setup of the learning algorithm and also different noise patterns on the pixels. So this just gives you some sensitivity idea of how sensitive each algorithm is to different starting cases, which should be nominally identical. It's worth mentioning here that the BitBrain results, these error bars are basically less than the thickness of the plot line. So you could describe this as a different form of robustness as well. So you can see here the same pattern. If you don't add any training noise, I don't know, can you see my cursor here?
Yes, we can.
Yes, you can. Okay, you can see if you don't add any training noise, there's a very sudden degradation of the test according to test noise here. As you add more training noise, there's some improvement, but again, they degrade after the amount of training noise is given. So we think this is a fairly typical pattern for an early CNN. And just to give you a graphical comparison, this is the BitBrain result on the top and the LINET5 result on the bottom. So you can see that there's quite a sharp difference in robustness here between the two cases. Okay, now you might say LINET5 is a very old CNN. That's not really fair. Okay, so here's a comparison with what could be arguably is a state of the art, or is at least a very recent CNN called CapsNet. Again, the same comparison. Now, we can't compete at the highest level here with CapsNet. You see CapsNet gets very close to 100% on MNIST, although it degrades with more test noise. But you can see there's variability in the results with CapsNet. You have to choose the right training noise level. There's still uncertainty. And of course, we do have to say the amount of training for CapsNet compared to BitBrain is an enormous difference. It's also worth mentioning that it's worth noting that if you use 120 standard deviations of training noise with CapsNet, you get an excellent result right across the test noise case. And this may be an interesting result in itself. It suggests that CapsNet can be very effectively regularized by using training noise. Okay, so now a different problem, a much tougher problem. This is EMNIST. This is now 62 classes and very unbalanced. And this is all digits, all lowercase and all uppercase digits in the same format as MNIST, as a 28 by 28 grayscale images. And it's a much tougher problem. And as you can see there's obvious aliasings between various things here, which will make it very difficult for any algorithm to identify between them. So we get just shy of 80% with no test noise, but as before, you degrade quite quickly if you use no training noise. But again, you see the same pattern. As you add training noise, you become less sensitive to test noise, although in this case, the degradation for the zero test noise case is sharper. Again, this is the comparison with LINET 5. You can see the amount of variation here, depending on random number seed, is huge. And the same pattern is shown as with the MNIST results. And this is the same comparison, but now with CapsNet. So CapsNet is itself struggling here. It's a pretty tough problem, but we can't compete with CapsNet, but do bear in mind the amount of training, energy, and time required for the two cases. So this arguably is a fairer comparison. This is a comparison on MNIST with other single pass methods. The red bars are CNNs trained with for just one epoch. And it's worth bearing in mind that even just for one epoch, there is a significant amount of extra training compared to what we're doing, because it's floating point and there's backpropagation, you're having to calculate derivatives and everything else. And the blue bars are methods specifically designed for single pass classification on MNIST. And I believe most of these are specializations of support vector machines, specialized for single pass. And in this case, we have the best performance. This is obviously all noise-free here. I thought I'd keep this simple because the noisy results weren't easy to generate for the other cases. So this is all noise-free, no noise in the training, no noise for the test. So these are results you're used to seeing for comparisons. And a second comparison with single pass methods. In this case now, this is two class problems. And using MNIST, there's a 0 versus 1 classification, and there's the 8 versus 9 classification. And I've reproduced a table from a paper that's referred to there. And you can see in this case that we do dominate the results. In fact, I don't believe libsvm even is on the left-hand side. I don't believe that is even single pass. I don't think that's a single pass method as far as I know, but I could be wrong. I have to go back and read the paper. And in the case of 8 versus 9, you can see that we actually, we're pretty far ahead of everything else in there. So again, as a single pass method, we're doing very well there. So I'd like now just to go through and some conclusions. There is a paper coming out which will have a lot more detail about this, both the motivation and the backgrounds. But I'd just like to really go over what I've said today so far. We have a novel single pass learning mechanism. The aim is accurate classification. It seems to be the best at the moment in single pass on MNIST. It has good robustness to imperfect inputs and other forms of uncertainty, which we feel is very important for AI and machine learning to be used out there in the wild, especially safety critical or where people can't supervise the learning mechanisms. It has simple and energy efficient operation. It's all small integer and bitwise. There's no floating point. There's no derivatives to calculate. To give an idea of speed, although well, let me say, well, first of all, it does 10K inferences 0.42 seconds on a current Apple ARM laptop, ARM M1, but this is single-threaded. And it's worth mentioning this doesn't leverage the GPU or any of the many opportunities for gains on neuromorphic hardware. In particular, the sparsity of the ADE firing, about 1% sparsity, the low resolution of bitwise computations, and the embarrassingly parallel nature of the algorithm are all a very nice fit to neuromorphic hardware. So we are expecting to see some very big speed ups once we implement it on more appropriate hardware. We have improved some we've investigated some other methods for improving inference, jitter and data augmentation, where we're moving the image around during training, and also using a non-uniform count of the bit counts, a non-uniform weighting of the bit counts, using some information from the occupancy. And both of these could independently gain about 1% on MNIST in a noise-free case. So the results I've shown you have been very much a raw mechanism, but we believe there are opportunities for improvement. And so some of these are the following. We want to do some more challenging 2D benchmarks using RGB rather than grayscale, CFAR 10-100, the German traffic sign database, and potentially as we get up to larger scale and more powerful implementations, ImageNet and such. We're looking at CNNs or other biologically inspired front ends to make the unsupervised phase less important, or maybe even not needed at all. So in other words, we put filters on the front of this and there's no unsupervised phase. That's a possibility that we're investigating. We are looking at continuous adaptive learning with or without forgetting. And as you can see, there are two cases here that are of main interest. One is that over time, the task or perhaps the sensor is degrading, or perhaps the patterns themselves are changing. Now, you can learn that, you can see that will be learned directly, no changes at all. If you want to have forgetting, as new labeled data comes in and you put in another 1,000 bits into the memory, you then randomly move 1,000 other bits. And over time, this will adapt over time to the new mechanism, to the new patterns, and gradually forget the old patterns if necessary, whilst keeping the same memory occupancy. The second case is you might need to learn different classes, in which this is very simple. You just add a new class to the memory. It's simple as that. So some problems which are actually quite tough for the traditional machine learning mechanisms are actually going to be dealt with relatively easily here. I'm interested in looking at layers of SPC memories. As we've seen from deep neural networks, as you add layers of fairly simple processing elements, you can get quite big changes in the inference performance. And one in particular, was touched on yesterday by the last talk by Kenneth Stewart about how you can learn pseudo classes, so you can learn unsupervised clusters. And this could be something that could be learned by the first stage SPC memory, and the second stage SPC memory could then use those as outputs, as inputs, and the class storage could be in the second layer of SPC memory. So we're interested in exploring all these ideas. We want to apply these to different types of data, time series data, DNA, biology data, abstract codes, and 3D volumetric medical images. There's a lot of potential for different types of data. For example, for time series and for event-based cameras, if you put different delays on different synaptic connections, you will automatically get spatiotemporal pattern classification. You now see that the spatiotemporal coincidences will be stored. So this is a very simple adaptation which will provide that as well. I want to look at more underlying theory. I'm particularly interested in the connection to kernel methods. There's a section in the paper on that, but also sparse distributed memories and vector symbolic architecture, vector function architecture. I think these all have some underlying relationship which may be interesting in understanding and improving the mechanisms. And of course, good mappings. We're currently just using these on normal computers, but good mappings to GPUs, FPGAs, Spinnaker in particular. This might be something we could do at Capicatcher called BitBrain on Spinnaker, might be a group we set up. Other neuromorphic platforms and even specialized hardware. And I'd just like to say that these are early results with fairly limited resources, but we hope that these results will become more impressive and broader over time as we put more resources into these ideas. And with that, I will thank you.